And as we said, if we make an electrochemical cell containing copper and zinc electrodes, the reaction occurs because copper has a greater tendency to accept electrons compared to zinc. How do we know that? We can figure it out using volts. Not only do we want to explain why copper is reduced and zinc is oxidized, but we want to compute the voltage of our battery. So to do that, we look at something called a standard reduction potential. So for a reduction reaction like this, scientists have measured the voltage that goes along with this reaction, and for copper ion picking up 2 electrons to form copper metal, the voltage is 0.34 volts. We call that a reduction potential because it's synchronized with a reduction reaction. It's a voltage that describes this reduction reaction. So the half cell for this reaction would look something like this. We would have a copper electrode immersed in a solution of copper ion. Usually that's going to be 1 molar at 25 degrees Celsius. I haven't shown the other half cell, but what happens here is that the copper ion in solution picks up electrons. Those electrons are going into it here and plates out as copper atoms. And this is the chemical reaction. That's the cell potential. How do we measure cell potentials like that voltage? To do that, we need a reference. Our reference is called the standard hydrogen electrode. It consists of a beaker with 1 molar H plus in it, and then a tube through which we pass hydrogen gas at 1 atmosphere pressure over a platinum electrode. And when this happens, the hydrogen ions in solution are reduced to form hydrogen gas, so we see a bubbling of H2 gas coming out. And scientists assigned a cell voltage or half cell voltage for this at 0 volts. So this is our reference point. So to get our voltages for all the different metals, we set up a cell where this is one of the 2 half cells and where its voltage is 0. For example, this is how we would measure the standard reduction potential for copper. We found 0.34 volts. There's our SHE. Its half cell voltage is 0. We measure the electrons are going in this direction. The copper ions plate out, and the voltmeter measures 0.34 volts, and we call that the standard reduction potential for copper, occurring under these conditions: 1 molar copper ion and 1 molar H plus. So we can change the copper electrode to zinc, manganese, nickel, all the different elements out there, and we can derive or measure the standard reduction potentials for all the metals in the periodic chart. Those standard reduction potentials are in a table like this. So there's tables for hundreds and hundreds of substances, but this standard reduction potential gives you a voltage for these reduction reactions. Every reaction written here is a reduction. It's something gaining electrons to form a metal, okay? Substances at the top of the table with the highest voltage are the most easily reduced. Substances at the bottom are less easily reduced and more oxidized. So if we put copper together with zinc to make an electrochemical cell, because the copper reduction has a higher reduction potential, it's going to be reduced. That's going to force the zinc to be oxidized because zinc is less positive, has a less positive reduction potential. Okay, so now let's look at zinc. This would be a half cell for zinc. This would be reduction for zinc. Zinc plus 2 electrons go to zinc metal, and if we measure this, it's a negative 0.76. Let me point out one thing here. For this reduction reaction, this is the reduction potential for zinc. If we reverse this reaction, we turn it around so that zinc is the reactant and Zn2 plus and 2e negative are products, this describes an oxidation. If we reverse a half reaction, then the true voltage is the reverse of the reduction potential. We get the reverse by changing the sign from negative 0.76 to 0.76, and now we call it an oxidation potential. But you'll see that I don't use these very often because it gets confusing. There's another way to solve problems without using oxidation potentials. All right, so here's our zinc copper electrochemical cell. This one has a complete circuit. Zinc is immersed in 1 molar zinc ion, copper in 1 molar copper ion. We said that the zinc goes into solution to make zinc ions. That's a oxidation. The extra electrons travel through the circuit to the copper. The copper ions pick those up and plate out. And to complete the circuit, the salt bridge allows ions to move in both directions. All right, let's calculate the cell voltage for the copper zinc half cell. So from our table of standard reduction potentials, these are the two reduction potential reactions for copper ion and zinc ion. The copper is 0.34 volts. The zinc was negative 0.76 volts. So we know that the copper ion is going to be reduced, and to make redox work, we're going to have to flip the second reaction, and zinc is going to be oxidized. So the way to get the standard reduction potential is take the higher of the two value, the more positive value, and subtract from it the less positive value, which is a negative 0.76. So 0.34 minus a minus 0.76 is a 1.1 volt. So my method of calculating cell potential is high minus low. You don't really need to translate a reduction potential to an oxidation potential before adding. You just take the high number minus the low number. So I showed you that. I have it again here. Only I'm going to show you one more thing here. I'm going to show you how to write the overall cell reaction equation. So given these two reduction potentials, we know that the copper ion is going to be reduced because it's more positive, and the zinc is actually going to be an oxidation. So we have to flip this reaction. So before we add these two reactions together, we reverse the second reaction. So here's our first one written as reduction, and there's our second one written as an oxidation. Now we add the two. Copper ion plus zinc goes to copper plus zinc ion. 2 electrons gained, 2 electrons lost. The electrons cancel, and the total cell voltage then is 0.34 minus a minus 0.76. I didn't change this to an oxidation potential. I kept these as reduction potentials, and I just took the high minus the low to get 1.1 volt. Here's our complete copper zinc electrochemical cell. On the left, the zinc is oxidized. On the right, the copper is reduced. Electrons flow in this direction, and the salt bridge allows ions to flow between the two cells, completing the circuit. And this is our overall cell reaction. Zinc is oxidized, the copper is reduced. By the way, our cell potential values do not depend on the number of electrons in the chemical equations. And here it is again. So zinc goes into solution as a zinc ion. The electrons that it lost go through the outer wire through the voltmeter to the cathode, where copper ions pick them up and plate out as copper atoms. We're going to use sodium sulfate as our background electrolyte. As copper ions plate out, we lose positive charge on the right side. What happens then is that the sodium ion from the background electrolyte migrate over and keep that right side electrically neutral. On the other hand, on the anode side, we have positive charge building up in that half cell, so it's becoming more positive. So our background electrolyte sulfate migrates over there to neutralize that positive charge and to keep the cell neutral. If we didn't have this background electrolyte there, we would have this side becoming more negative and this side becoming more positive. When this electrode gets to be more and more positive, it pulls the electrons and prevents them from flowing to the other side. And as the other side gets more negative, it repels the electron. So if we don't have a salt bridge, then what will happen is that this side will become more positive and this side will become more negative, and the reaction will stop. So the salt bridge is absolutely necessary with background electrolyte. We need the salt bridge to allow migration of background electrolyte. We need background electrolyte to neutralize the charges that are forming or being lost So with that cell that I've shown here, instead of drawing a picture, there's a shorthand way of drawing a schematic for that cell. It's called a cell diagram. We go with anode on the left side and cathode on the right side. So zinc in a solid state is our anode. It's separated by a metal to aqueous phase boundary, a single line. And in that aqueous phase we have 1 molar zinc ion. This is the first half cell. It's separated from the second half cell by a salt bridge. And the aqueous phase in that second half cell contains copper ion at 1 molar, and there's the phase boundary between that aqueous solution and copper solid in the cathode electron. On this page, we're going to talk about how to compute the free energy change for a redox reaction. So again, reviewing back thermodynamics, if delta G for a reaction is negative, that means it's spontaneous. And if delta G is positive, then the reaction is non-spontaneous. This is the equation that we use to calculate free energy change for a redox reaction, minus NFE. N is the number of moles of electrons that are transferred. F is a constant equal to 96,500 joules per volt per mole. And E0 is the cell potential in volts. For our copper zinc reaction, remember we measured the cell potential to be 1.1 volts, and we had 2 moles of electrons being transferred, 2 moles of electrons gained, 2 lost, so minus 2 for N. There's our Faraday's constant. Notice that the moles cancel, and that the volts cancel. We're left with joules. We end up with minus 212, 300 joules, or minus 212 kilojoules. It's negative, so it's a spontaneous change. When E0 for a cell is positive, that means that delta G is negative and the reaction is spontaneous. Right, here's an example. A Voltaic cell contains a gold electrode immersed in 1 molar of gold cation and an iron electrode immersed in 1 molar iron 3 solution. We want to explain the cell. In other words, we want to compute the cell potential, write the reaction, draw a cell diagram, and compute the free energy change. So we look up our 2 reduction reactions. Here's the first one. There's our cell voltage, or half cell voltage for that. The second reduction is this, negative 0.037 volts. Just from these 2 numbers, we can tell that the gold cation is going to be reduced and the second reaction is going to be an oxidation. We know that because this number is more positive than that number there. So the reaction that occurs is this. We write the gold cation reduction just as it's given, but we reverse the iron reaction, so we get iron going to Fe 3 plus 3 electrons. That's an oxidation. We add those up. We have 3 electrons gained and 3 lost. They cancel. So our overall reaction is this. And our cell potential is going to be high minus low. Minus a minus 0.037. You'll see that the gold cation is being reduced and the iron is being oxidized. Our free energy change for this is going to be minus NFE minus 3 moles times F times and the reaction is spontaneous. What would our cell picture look like? We have 2 beakers, and not a very good drawing. We have 2 beakers with some liquid in them. There's one electrode, there's the other electrode, there's a voltmeter, some wires connecting them together. And we know that the gold is being reduced. So there's our gold. And then this must be our iron 3 cation, our iron electrode. This is going to be our anode. This is going to be our cathode here. And electrons flow in that direction. And the reaction here, of course, is Fe. A second example, electrochemical cell made from silver and nickel. So the reduction reactions would be this and we need to look up the cell potentials for these 2 reactions. For the first reduction, E0 is plus, and for the nickel, so we know we need to flip the second reaction and make it an oxidation. So then overall we have we need to add these up, but we notice that the number of electrons lost and gained are not balanced. We have 1 electron gained and 2 lost. To make them equal, we'll multiply the first equation through by a 2. Now we have 2 electrons gained and 2 lost. They cancel out. We can add up. That's our overall cell reaction. And our cell potential is going to be high minus the low. Our free energy change is going to be minus 2. Next up is the Nernst equation. The Nernst equation tells us how to calculate the cell potential for a reaction which may not be at equilibrium. So the cell potential is equal to the standard cell potential plus this correction term, which contains Q. Remember, that's similar to the equilibrium constant, but pertains for a system not at equilibrium. We have a coefficient of 0.0592 over n. N is the number of electrons transferred. This 0.0592, you don't need to know where it came from, but it comes from this equation up here. It's RT over F. We're going to do all of our experiments at 25 Celsius or 298 Kelvin. So T is 298, R is 8.314. To change ln to log, we multiply by 2.303, and we divide by F. If we go through that, we get this number here, okay? And then this becomes the Nernst equation. Q for this equilibrium here would look like this, products over reactant. So utilizing the Nernst equation, let's go back to our copper-zinc reaction. This is what the Nernst equation would look like for that situation. Only we know that we can insert n equal to 2. The Q term here is going to be the zinc ion concentration over the copper ion concentration. We don't include metal solids in an equilibrium constant expression because their concentrations are constant and do not change. They're not part of the dynamic reacting system. So we only include dissolved ions. Products over reactants, the stoichiometric coefficients are 1, so the powers are. Right, we already calculated what E0 was earlier, 1.10 volts. and we found that N was equal to 2. Let's calculate the cell potential when the zinc and copper ion concentrations are the same. We get when the concentrations are the same, they cancel out. Log of 1 is 0. The second term drops out. E is equal to E0, close to 1.10 volts. Let's take case D here. When the zinc ion concentration is 1/10 the copper ion concentration. It's zinc over copper, so we would have 0.1 here. Log of 0.1 is -1. We get 1.10 plus 0.0592 over 2. Equilibrium. When we have an electrochemical cell, it turns out that we can derive this equation, which we actually saw in thermodynamics. Delta G equals delta G0 plus RT ln of Q. At equilibrium, the free energy change is 0, and Q is equal to K, so we can put K in here. But we know from before that delta G under standard conditions is minus NFE. So we can actually take minus RT ln of K instead of equal to minus NFE. The minus signs cancel out. Ln of K then is NFE over RT. RT over F is 0.0592. So ln of K is equal to this. Take both sides to base E, and we get this here. Okay, allows us to calculate equilibrium constant from cell potential. And this allows, this equation up here allows us to calculate E0 from ln of K. We could say that E0 would be RT ln of K over NF. Electrolysis. It's a galvanic cell operating in reverse. It's a reaction in which we pump electricity into a cell to make a non-spontaneous reaction occur. Current is forced to flow through the cell in an opposite direction that it would normally flow. And that usually causes something to plate out on top of something else. Here's a schematic for an electrolysis cell setup. Again, we have two half cells separated by some kind of a phase boundary, permeable phase boundary allowing cations and anions to pass through. Here's our zinc electrode, there's our copper electrode there. And this time we have an external power source or battery. I hooked up the negative electrode to this electrode here, making this one negative. The positive pole on the battery is connected to this second electrode, making it positive as well. So we're pumping electrons into this side here, causing the zinc ions to plate out as zinc. This side is increasing mass, and the other side is losing mass. What we would like to do is calculate how much zinc is actually plated out on the surface of this electrode in a certain amount of time after we pass a certain amount of electrical current into this cell here. So to do that, we need this information. Faraday's constant, 1 mole of electrons carries a charge of 96,485 coulombs, close to 96,500, and we call that 1 Faraday. It's really the charge on 1 mole of electrons. One electron has this charge, coulombs per electron. 1 mole has this number of electrons per mole. We multiply the two numbers together and we get Faraday's constant. We can calculate the number of moles of electrons transferred using this equation here. The current times the time over 96,500 electrons per mole. I is coulombs per second. Time is in seconds. So we have coulombs on the top here. In the bottom we have coulombs per mole. So we can calculate moles. Example. Given our cell that we've seen before, how many grams of zinc are plated out when 10 amps of current are passed through the cell in 100 hours? So for zinc plating out, That would be this reaction here, a reduction of zinc ion to zinc metal. And we know that 2 moles of electrons convert 1 mole of zinc ion to 1 mole of zinc. So 2 moles of electrons convert 1 mole of zinc cation to 1 mole of zinc metal. Or X moles of electrons convert X moles of zinc ion to X moles of zinc metal. We simply need to find the moles of electrons passing through our circuit using this number here. So if we find out that we have 2 moles passing through our circuit, then we get 1 mole of zinc. So here's a schematic on the calculation. We'll change current to Coulomb. We'll use the Faraday's constant and then convert moles of reactant to moles of product. We're told that we have I is 10 ampere, so we have 10 amps or 10 coulombs per second passing through the cell for 100 hours. We need this time in seconds, so we multiply by 3,600 seconds per hour. That's going to give us the number of coulombs passing through the cell. We multiply by 1 over Faraday's constant. 1 mole of electrons is equivalent to 96,500 coulombs. That'll tell us the number of moles of electrons. And from our equation up here, we know that 2 moles of zinc are produced, or 1 mole of zinc is produced from 2 moles of electrons. And then we look up the atomic weight of zinc and multiply by to get the mass of zinc plated out. So our calculation is 10 coulombs per second times 100 hours times 3,600 seconds per hour divided by 96,500 divided by 2 times 65.4. That gives us around 12-20 grams. It's so high because we're going for 100. That's almost 1.2 kilograms. Second example, compute the number of grams of aluminum plated out in 1 hour by passing a 10 amp current through the cell. We have 10 coulombs per second going through the cell for 1 hour, and we have 3,600 seconds in an hour. That tells us the total number of coulombs going into the cell. We multiply then by 1 mole of electrons per 96,500 coulombs. That'll cancel out the coulombs and tell us the number of moles of electrons. From our chemical equation, we get 1 mole of aluminum from 3 moles of electrons. So 1 mole of Al times 3 moles of electrons, and multiply by the atomic weight of aluminum, which is close to 27 grams per mole. And we get plated out. And that's pretty much it for this chapter.